Right, welcome everyone to today's UK Metamaterials Network Colloquium. I'm Anja Roding. I'm the Operations and Relations Lead of the network. In case you're not aware of it yet, we'll put the link to the network website in the chat. So please feel free to have a nose around, sign up if you'd like to participate. It's an open signed network for researchers and academia in non-academic institutions across the UK and beyond, for running events, to participate in colloquia as much like this one, to share experiences and knowledge as much as possible. So feel free to sign up, or if you have any questions, do get in touch with us and we're happy to answer any inquiries you may have if we can. So on that note, I would like to introduce today's guest speaker. You're about to hear a talk from Fabrizio Scarpa. Fabrizio is Professor of Smart Materials and Structures at the University of Bristol, and also Materials Theme Leader at the Bristol Composites Institute. So his research interest spans the fields of metamaterials, nanocomposites, materials for vibroacoustics and energy dissipation, as well as sustainable and recycled structures. So those activities are supported by projects funded by EPSRC, the EU. He just mentioned he's got a new grant in, DCL, the ONR and industrial collaborators. And Fabrizio is also grant holder of an European Research Council advanced grant on the field of neuroactive bio-based mechanical metamaterials. He's been working on mechanical metamaterials, so auxetics in particular, long before they were called metamaterials. And I'm very, very pleased to have him as part of the leadership team on the UK Metamaterials Network, and even more happy to have him here today to speak to you.
Thank you very much, Anja, and thanks very for the nice introduction. And thanks to everybody really attending this seminar. I will talk about fractality, Kirigami, and patterns, and especially within the context of architectures for potential bio-inspired metamaterials. I will start with a very broad intro motivation about metamaterials, especially mechanical metamaterials. Then I will dig into more fractals, Kirigami concepts, Chiral fractal metamaterials. I will then talk about Hilbert fractals and coiled metamaterials for sound management, especially as a sort of case. Something more on the natural side, I will mention some results that we obtained on cactus fibers and fractality related to cactus fibers. And then I will finish with some consideration about fractal surfaces for contact stiffness and friction. I think really the audience of this seminar is very well aware of what is a mechanical metamaterial, but just really to give a general introduction, we are talking about composite and multi-scale structures made with lattice architectures, also multiple phase materials architectures. In general, their microstructure geometry and their materials distribution can lead to unusual mechanical properties for negative Poisson's ratio, stiffness, compressibility, and mass, and not only those type of unusual or negative type of properties. They can also be produced using 3D printing, microfabrication, and also other types already of techniques. And most of the images that I show you really in these slides are related to classes of mechanical metamaterials that have been developed really since 2002, 2003. But there was also a previous work done, especially on negative Poisson's ratio materials and lattices, going back really to Rod Lakes and back in 1987, and not only Rod Lakes, also Ken Evans from Exeter. So that's the reason why people working especially negative Poisson's ratio and that are now considered mechanical metamaterials can claim that there's been starting to work on those type of materials before the term mechanical metamaterials was coined. Something interesting regarding to fractality is the concept of fractal geometry has been already used for metamaterials. I would say that one of the first papers is this a conference paper on transparent optical network back in 2018. And especially for electromagnetic application, fractal configuration have been developed to design antennas, especially multiband flexible antennas with matching impedance. And the fractality is very useful, especially to optimize the surface area of this type of antennas. So you can minimize the dimensions of the antennas and still obtain this multiband flexible matching impedance. Also, similar consideration for electromagnetics have been also used to design surface wave absorbers for acoustics. And there is this quite famous paper from Song and co-authors in APL back in 2016 that was already showing some this type of tunable characteristics by using only fractal distributions in acoustic absorbers for surface waves. Fractality actually has been historically considered also to model earthing contact and roughness, and this comes back really at least to 3 or 4 decades. But less focus has been put on other mechanical properties. Fractal patterns need to be built. I already mentioned before that it's possible to use 3D printing, additive manufacturing, but something much more ancient and in principle also more adaptable to different types of substrates is the Kirigami approach. Kirigami comes from the term of the ancient Japanese art of cutting and folding paper that was spread in Eastern Asia since the 17th century, but actually we may argue that Kirigami has even older origins from the Chinese Zhenzhe. I really apologize to all the all Mandarin Chinese speakers of the audience, but the Zhenzhe is in essence is paper cutting. As an art was already spread in China since the 6th century. And Kirigami is a mix between origami and cut patterns. Actually, probably Kirigami involves more the design of the folding and hinging associated really to the folds. Paper cutting is more related to the use really of cuts, architected cuts to create really the structure. And cuts and perforation have been used in the metamaterials community during the last decade to create classes of metamaterials, especially configuration that exhibit a negative Poisson's ratio. And I show some examples of different types of Kagome square cut patterns that they were developed by the Bertoldi group. And there is this quite famous paper in Mechanics Letters in 2015 that was already showing the different capabilities of Kagome square cut patterns. At the same time, we were developing also those type of square patterns that some of them were actually inspired, especially to the rotating rectangles concept that Joseph Grima and Ken Evans, they pioneered early a few years ago. One of the big advantages of using this kind of cutter perforation is you can virtually use any type of substrate if you use the correct manufacturing process. Most is a laser cut, but also the simply cutters already they make the job depending on the type of substrate, whether it is metal or elastomeric. You can also tessellate gradient configurations. And it's possible to construct also hierarchical fractal architectures by using this type of Kirigami cuts approaches. And I chose here an example of sort of a nested perforated metamaterial that we have published some time ago. We take the central square pattern perforation that actually was first identified by Ole Sigmund via topology optimization more than 20 years ago. If we repeat the same pattern on the rotating rectangles that we see on the four sides of the unit cell at different levels, we can recreate this type of nested or hierarchical configuration. And this configuration actually has got some interesting mechanical characteristics compared to the baseline one. First of all, the baseline one, or level one, is an auxetic metamaterial, but when you go especially to large interspace distances between the different perforation, we are talking about a parameter S, so goes from 0 to 1 is the interspace between the perforation. When we go for this type of relatively large values of the interspace, the configuration tends to go towards a sort of a zero concentration effect. Every time that we adopt a hierarchical configuration, we always obtain an auxetic, negative concentration configuration, spatial orthotropic, but always auxetic. You see the discontinuities over there on the different engineering constants that are calculated using asymptotic homogenization by finite elements. Over there for this value of S 0.5, and this is because for this interspace ratio, we have a sort of a transition of the sort of the mechanism that goes from pure stretching to pure hinging at the interface over there. You can also see that we obtain always different in-plane compliance. The structure becomes extremely soft. But this is also one of the reasons why it can be quite interesting also for band gap and wave propagation control, especially lower frequencies. Here you see some wave propagation, wave dispersions in the first Boolean zone for this type of configuration calculated using block wave techniques, classical ones. We have normalized the frequencies of the dispersion versus the frequency of a homogenized plate with the same porosity and mechanical properties. You can see that the level one configuration has already a very nice band gap behavior, also quite large. As soon as we go to the second one, we start to increase the flexibility. So we start also to see quite a lot of wave dispersion at lower normalized frequencies, but we also increase the number of band gaps. They are not so large as the single one, but you start to have multiple band gaps. When you go, for example, to order 3, you obtain even a richer band gap behavior. And this is also seen quite clearly when you try to plot or to map the amplitude and the number of band gaps versus the different aspect ratios of the perforation and also interspace distance. There is something that I need to warn you. You cannot simply reproduce this type of dynamic behavior by asymptotic homogenization. If you try to calculate really the dispersion curves using Christopher's Schwarz equation. You can still obtain a fairly decent match between high fidelity block wave and homogenized dispersion for the first level. But as soon as you increase the order of the nesting, the match is not there anymore. Something that is also interesting, if you use a box count technique to try to identify a sort of a fractal order for this configuration, you will have fractal orders ranging between 1.7 and also 1.8, 1.9, and they are very much dependent upon the interspace distance. This is a configuration that actually, in terms of tunability, may be quite interesting. But at the same time, please be aware that simple asymptotic homogenization is not sufficient to provide you a really very good picture of the dynamics of this kind of architecture. Another type of fractality that we have developed for metamaterials is this chiral fractal configuration. The fractal curve that you see over there is a self-filling space, is a Peano's curve by mirror symmetry. And there are quite a lot of resemblance with the sort of a chiral metamaterials that you have seen really in open literature during the last 2 decades. It can be created by any type of substrate. The example that you see over there is simply really a wood plate, and we have cut really the substrate using a laser cut. On the net, sometimes it is also indicated as wood rubber, and the simple reason is if you take a plywood plate and you cut in this way, then you deform. The deformation will really be very much similar to the one of a sort of a rubber or elastomeric plate. The mechanics of this kind of configuration haven't been explored particularly, and in this International Journal of Solid and Structures paper that we produced already almost 4 years ago, we considered an analytical model that was based on using either Euler-Bernoulli or Timoshenko-Bernoulli or shear beams, fixed shear beams, to consider a sort of a continuous pattern describing this chiral fractal metamaterial, and also with a finite element simulation. We did also some STM test on tension and also shear ±45 on Perspex samples. And as you can see, we obtain also some fairly good comparison between experiments and results. You can also notice that the Poisson's ratio is negative, but only is marginally exotic, it is very small. The interesting bit is you have in this kind of configuration a very strong interplay between the shear deformation of the beams making the chiral fractal and also the flexural bending of the same beams. And based on the different approaches that you take, you may obtain some different mechanical characteristics. For the highest orders of the fractals, so the ratio A over B between the dimension of the beams and the whole dimension of the cells, so you tend to obtain chiral fractal cells with very much slender beams. So the difference and the effect given by the shear is less strong. Something that actually is also quite interesting is if you plot really the logarithm of the normalized Young's modulus versus the inverse of this ratio AB that defines really the fractal configuration, you will have a perfect line. And this is an excellent indication that effectively, like fractal physical quantities, this type of configuration really has got this type of exponential variation of the mechanical properties with the order. So, and this is really, again, typical of fractal units. Another interesting bit is for this ratio A, B equal to 10, even higher, if you look at other type of cut patterns, metamaterials that you find in open literature, like, for example, those that I showed before from Bertoldi's group, you will see that compared to the plates made with the bulk material only, you start to have some resulting Young's modulus, which are a lot lower compared to similar configuration shown in open literature. In other words, for the same porosity, configuration in open literature, they tend to have between 4 and 16% of the initial Young's modulus. These configurations are a lot lower, up to 0.4 and 0.5%. So if you want to introduce compliance, shape morphing, a lot of flexibility, this type of fractal configuration are quite interesting. And the same type of behavior, especially at lower frequencies in terms of band gap, that we have seen in the nested hierarchical metamaterials, is also existing in this kind of fractal metamaterials. Over there, you can see some block wave propagation analysis that we have done. The interesting bit is, if you look really at the first level, practically you don't have really a band gap, or you start to have very narrow band gaps, especially higher frequencies. The more you increase the fractal order, you start to create these larger band gaps. And actually, interesting enough, those larger band gaps tend to be created at higher frequencies, not so much at lower frequencies. So this is another feature that could be really interesting to consider, whether you need to create those band gaps at different frequency bandwidths, higher or lower compared to the previous nested metamaterials concept. We also more recently explored the energy dissipation capabilities of these chiral fractal metamaterials under bending. So we have built those samples. Those samples are actually created via 3D printing. We have used a thermoset very white material. The bending is quasi-static but cyclic, so very low, is around 0.1 Hertz. We have considered 3 fractal orders, 10 thickness samples, 10 samples with different thicknesses, subjected to each to 10 maximum central deflections. And we have also developed finite element models that consider the viscoelasticity and also the contact stiffness and friction that exist between the vertical walls of the cells when you start to bend in the middle. The comparison between the finite elements and the experiment is quite good. And also in terms of energy dissipated, you can see that it follows this type of loss scale of the fractal order that we have seen before. If you compute the loss factor, which is proportional to the ratio between the energy dissipated and the energy that you have inputted into the system, you will see that actually the loss factors tend to be quite constant with the fractal order. And this is also something that is quite interesting. We haven't seen this feature in this architecture, but we have also observed a similar feature in another type of fractal architecture. So something really very much really yet to be explored, but quite interesting. And the bending stiffness and the energy absorbed, the loss factor, they have all a sort of a nonlinear dependence with the thickness of the beams. And the loss factors, especially for very thick fractal beams, they look, it looks like that has got a sort of a minimum and then stabilize. And this is due to the fact that some of the features given really by the fractal order in terms of contact friction between the vertical walls need also to be balanced by the viscoelasticity of the core material itself. So you need to be careful when you select the material to make this kind of architected metamaterials in terms of energy dissipation, because you also need to consider every type of micromechanism existing at materials level interacting with the architecture itself. From the sound management point of view, I'm talking about especially in terms of acoustics, fractals or metamaterials can have a role. As I mentioned before, that in terms of electromagnetics, these types of configuration that this is an Hilbert fractal and this is a coiled type of, is not really a fractal, but is a coiled metamaterial architecture, have been already evaluated. They haven't been evaluated so far in terms of acoustic absorption in impedance tube, also via finite elements. The two configurations that you see over there, this is a Hilbert fractal self-filling space. And this one, they have the total length of the cavities equal. So we have considered these two configurations really as a benchmark to assess whether really fractality plays a role in the acoustic absorption. So we have done a really test in impedance tubes and develop also finite element models considering really pure acoustics and also viscothermal acoustics with a sort of boundary layers, especially at the interface of the internal cavity. Something that is interesting is if you look really at the sound absorption simulated inside an impedance tube, there is no difference between the Hilbert fractal and the coiled architecture, which is not fractal. But again, the two architectures, they have the same length in terms of cavities. So what is important from a sound absorption point of view is the volume of the cavity. So the length of the cavity, especially really the depth of the cavity itself. From the experimental point of view, you can see really some differences, and that also depends really on the specific setup of the impedance tube. And in general, we can also see that the trends between finite elements and experiments, they follow pretty much really the same pattern. But what is important really to keep in mind is the behavior between these Hilbert fractal, the core architecture, are the same, at least theoretically. And also you can create, by tuning the patterns, these peaks in terms of acoustic absorption. And those peaks, they correspond to the resonance of the air cavities inside the fractal. Something that I also like really to stress is you can see here in this plot the resonance is calculated simply considering the cavities, the air cavities inside the fractals, and those calculated using the finite elements simulated impedance tube. And the presence of viscosity in the air, especially inside the cavity, is quite important to get you really something that is comparable to the experiments. And actually, this is a fairly well-known fact if you want to simulate, for example, the acoustics of perforated panels. In perforated panels, you need always to consider in the simulation any kind of viscothermal effects. Not every cavity resonance inside the air or the fractal will provide you the peak of the absorption. You need to consider those modes that tend to have the maximum difference between the inlet velocity and the velocity in the middle of the fractal. These two configurations, as I mentioned before, they have identical cavity volumes, so they have the same tortuosity and cavity resonances. And you can see that the coil geometry Hilbert fractal will still provide the same behavior, but the peaks in acoustic absorption only happen when you have this maximum difference between inlet and inside. So for example, if you look at the absorption coefficient, you will tend to have, for example, peak absorption at that frequency at 792 Hertz, and then also peak absorption at that frequency at 1600 Hertz, but not another frequency corresponding to that peak. So this is quite important. It actually provides a guideline on how to design this fractal or tortuous type of metamaterials for acoustics. Where fractals still are interesting is the fact that a fractal by definition is a self-filling curve in space. So if you need to optimize your cross-section of the acoustic metamaterials, a fractal will still provide you a better use of the space that you have available. At the beginning, I mentioned that actually we have also quite a lot of examples really of fractality in nature, and I want really to report this work that we have done on cactus fibers, or fibers extracted by the rackets on the prickle pear. Something that we have discovered is that if you look really at the different scales of the fiber or the prickle pear, you will identify a sort of a constant fractal order around 1.8. And within a series of projects that we have also run with DSTL, we have then developed some rapid prototyping beams that were equating or trying really to simulate the fractal pattern of the cactus fibers. And what we have observed was that those fibers, experimentally, the real ones, but also the sort of the surrogate ones, they do all show a ratio between bending stiffness and the axial stiffness between 6 and 8, which is quite unusual in open literature, because a normal composite, they tend to have a really bending stiffnesses ratios between bending stiffness and axial stiffness are about 1.2. In some three-dimensional woven, you can start to have really something higher, but those type of ratios are quite unusual. And you can also see these are experiments really performed of 3D point bending with the scaled dimensions. Why this kind of behavior happens? Well, actually, if you look at the microstructure of these cactus fibers, that they have a tree-like fractal configuration, at the fundamental level, every fibril can be represented by this type of cellular tubular configuration. And if you do already the ratio between the bending stiffness and the axial stiffness of these cellular tubes, you obtain ratios between 5 and 7 and 6. When you bundle them in hexagonal packing, this bending to axial stiffness decreases significantly, it goes only to 2.5. But when you look then at the tree-like structure with primary and secondary structures that exist over there, and you make an estimation really of the distribution of the bending stiffness ratios versus the axial one, you come back to this value 6.7. So effectively, you have this type of different micromechanism for the deformation of the scatters fibers that really interact at different levels, and at the end, they provide this type of behavior. I will finish this seminar mentioning something that, again, was quite known for a while in open literature. Actually, if you scavenge really works on Hertzian contact in over a rough surface, quite a lot of authors during the already 40 years ago, they consider, for example, fractality for patterns of the rough surfaces. But what is interesting is not only you can control the contact stiffness with the fractal order, but you can also control the friction and the energy dissipation. So in these papers, a few years ago, we introduced this model that was considering different geometrical aspects of the average rough surface through a mean plate, a rigid plate, and also this D factor that is the fractal order of the surface that we consider. And we built also this rig to try to measure the contact stiffness also during a dynamic loading for dovetail blades at the base. So we use laser vibrometers and inverse identification using also finite elements, in which we applied these contact surface models. And quite interesting, in terms of really contact stiffness, if you want to really to increase the contact stiffness, you want to increase the fractal order of the asperities. And you can clearly see that, especially in this relation with the normal contact load. With the contact asperity, you also increase the equivalent friction coefficient. And friction actually is an excellent way to dissipate energy, especially at low frequencies. We also modified the model to consider this parameter alpha that relates really the contact stiffness to the normal force. And you can see there is a good agreement, but the take-home message is the contact stiffness really follows for this type of fractal surface a power law. So you have this type of power law that transmits in terms of topology of the fractality, but also, if you want, to really shape of the matrix or the mechanical response that you are looking at. And with this, I want to really thank you for your attention, and the funding agencies, but especially all my co-authors and collaborators over the years that have helped really to get really some of these results. Thank you very much for your kind attention.
Thank you very much for the talk, Fabrizio. It's such a pleasure to listen to you. I've just noted we've got 55 participants in the room, and I'd like to encourage everyone who would want to ask any questions to either type them in the chat or raise your hand, share your video if you can, so we can have a bit of a conversation rather than talking to a bit of an anonymous wall. There's always a risk that, you know, online engagement is, well, a bit one way. I've noticed there was quite a few of the leadership team members of the Metamaterials Network in the room as well. Let me just look at the chat. Right, so are there any questions from the audience at this stage? Technology doesn't break out. Mariam, would you like to ask your question via video by unmuting yourself? To make
it's the relation between Poisson's ratio and S. Okay, so I'll share the screen again. So, thanks for the question. But first I need to go to the presentation. I guess your question is related to this.
Hello.
Hello.
Yes, thank you so much for your interesting seminar. It was amazing. I enjoyed a lot. And yes, exactly here. It's I was like looking for the other, so I didn't maybe get the points here. So I see with the changing this, let's say, fractal ratio in these figures. Yes. The Poisson ratio, it's near to minus, like less than -1. I didn't get this point here.
Okay. Thanks very much, really, for your kind words. The first thing is this parameter S is not a parameter of fractality. Is the interspace.
Okay.
The interspace between the perforation.
Ah, okay.
Okay.
Yeah.
So we talk about fractality or hierarchical nested distribution simply by taking the unit over there and then transferring the unit into the original big bulk rectangle. Okay, so every time that we find really a bulk rectangle over there, let me.
Yes.
Okay. So you imagine to take these units and placing again your units again at different levels in self-similarity into the rectangle. Okay, so that is the sort of the fractal concept. But S is the distance between the perforation. Okay.
Got it. Yes.
And S so is something that we maintain constant at every level of the fractality.
Okay.
Okay, so the S that we use at the level 1 in the main one is the same S that we use inside there.
Ah, okay, okay.
Okay.
Yeah.
These are ratios. Okay.
Okay. Perfect.
And then you have this kind of discontinuity because in essence we are changing really the geometry over there for S05 in such a way that the small piece, if you want, that makes really the link, then it becomes smaller, and you have a sort of the creation of an edge. Okay.
Yes.
So it's a question. It's a question really of compatibility of the nested geometries one inside the other.
Okay, and here we see the Poisson ratio, like for a case, let's say S 0.3. We see this red like level 2, if I'm right.
Yes.
is written like a less than -1 for this case.
Now, over there is around, that value is around minus 0.48, 49. Okay?
Yeah,
the -1 is there.
Yeah, the below case. I mean, this.
Yes.
This
is a -1. Okay.
Yeah. So, like
So
obtain
okay, so this one is the Poisson's ratio when we go to the third level. So we have one cell inside the cell inside the cell.
Okay. So it's around -1.5 if I'm right. Yes.
Is around -1.5. These are special orthotropic materials. So
yeah.
It's perfectly possible to have this kind of values.
Okay, it's interesting. So, but is like in this case, the isotropy, let's say,
there is as soon as you start to create these nested metamaterials, you don't have a real isotropy. Okay. You have a special orthotropic materials.
Yeah. It's
okay.
Yeah.
In fairness, if you really want to do a better job in terms of micromechanical modeling, you should treat this type of nested metamaterials as a micropolar material or Coursera material, because in essence, you have the central node over there.
Okay. Yes.
That acts as a sort of a rotational unit.
Yes.
So now you probably know that chiral structural metamaterials, now they tend to be more and more modeled as a Coursera media because you have the rotation.
Exactly.
And in essence, every time that we create this unit inside the unit, we favor the rotation.
Yeah, exactly. Okay. Thank you so much.
You're welcome.
Thank you.
Mariam, before we move on to the next question, just a quick one. Whereabouts are you based and what are you working on?
I'm working on metamaterial, and I work also on acoustic metamaterial actually now. So I have some publication for this case. Now I am starting to work on non-linearity related to metamaterial and tunability of these structures. So like the wave propagation and this material I'm working.
Thank you. Thanks for the question as well.
Thank you so much. Thank you.
I think Alistair just unmuted himself and he's posted a question in the chat. If I may introduce Alistair as the PI of this network, whilst he's here, just turning on this video. Alistair, would you like to repeat your question for everyone?
Yeah, we've got a piece of work where we're using impedance tubes at the moment, and I was interested your data from the absorption coefficient. I was interested in just looking over again. What are the features which are due to the Helmholtz resonator mode? I think that's what they are. The peaks are they, and you're kind of modifying the ratio of velocities in order to move that and enhance that feature around. Have I understood that correctly?
Yeah. Okay. So in terms of impedance tube, we have used a 4 microphones impedance tube. Okay, with rectangular cross section.
I can see the diagram now. Yeah, the photo.
Yeah. Okay. Yeah, the photo. Okay, and well, we use a tube with a rectangular cross section because you may appreciate over there that we have a 3D printed really rectangular samples. So essentially, we can slot in really the samples directly with this type of shape. Now, probably here you can see really a better explanation, maybe really of what is going on. In essence, for this type of metamaterials, you can calculate the internal cavity volumes and the total length, and you will obtain different resonance frequencies. So effectively, you have Helmholtz resonator effects. Okay. Now, already, if you deploy the length of those cavities between this configuration and that configuration, actually, let me put the laser pointer. So between these two configurations, the lengths are the same. The width is the same. So in essence, we are talking about exactly the same internal fluid cavities. Okay. And in that sense, you expect, let me take out the, sorry if I move from one or the other, but with Zoom, I have all the small windows for, like this. Okay, so sorry guys. So you have these interesting peaks in terms really of acoustic absorption, and those depend really on the internal cavity resonators. However, if you consider all the possible modes that you can calculate from those cavities, not all the modes, they provide the peak absorption. And this is where you need to go. You need to look at modes that in essence, they provide you a sort of a polar behavior. In other words, you need to look at the modes that maximize the difference in terms of root mean square velocity between the inlet and inside the cavities. Okay.
Okay.
So but from an acoustic absorption point of view, whether you use this configuration or the Hilbert fractal, there is no difference, theoretical difference. Where the fractal starts to be interesting is if you need really to optimize really the cross-section of your metamaterial, because it's a self-fulfilling space.
Yeah. Okay.
Okay.
That's great. Yeah, that's explained. That's helped a lot. Thank you.
You're welcome.
Lovely. So are there any other questions of the from the audience? I think a few people have left us already, jumping to the next meetings or a lunch break, I assume.
Lunch. I'm really sorry, ladies and gentlemen, that I'm really, the last hurdle between your lunch and everything else, okay?
Well, given that they all turned off the videos, I would hope they eat whilst you spoke, but never mind. Right, okay, so if there's any other question at this stage, shout now. Otherwise, we shall close the session for today. 3, 2, 1. Okay, right. So on that note, I'd like to thank again Fabrizio for giving that talk. It will be on YouTube, on the Metamaterials YouTube channel, so you can find it there and rewatch it there, probably next week. And thanks also to Kellen, who organized this colloquium, and we'll see you again, I think, next month to our next colloquium, if and when. We'll communicate that through our usual channels on the website, Twitter, email. You'll hear about it. Thanks for joining, everyone.
Bye-bye.